Good evening, everyone. Thank you for coming. Thank you for attending this workshop. My name is Cyrille Molina. I'm the president of Oakridge, which is a multidisciplinary engineering and consulting company working in nuclear sector only for 23 years. And we do intervene in the new build projects for big units and also AMRs and SMRs. We're going to talk about it soon. And for the installed base and globally. I'm so glad to have great speakers today with Mr. Kiwhan Chung and with Mr. Aurélien Ledieu, our guest speaker from Nigeria, and the Vice President of Oakridge, Mr. Sivault. The title of the workshop is Worth Their Salt, because we want to show you the diversity of the work we've done with the Gen 4 reactors and with numerous clients developing their Gen 4 reactors. And we're going to have also the testimony from one of the clients, which is Nigeria, thanks to Aurélien. First of all, I will give the floor to Dr. Chung. And then once you finish, you give me the mic back, please. Okay, the floor is yours. Thank you.
Thank you very much for the kind introduction. My name is Kiwhan Chung. I'm in charge of neutronics calculation group at Oakridge. So it's my pleasure to introduce to and showcase our capability in Gen 4 reactor development. And okay, so my talk is we'll start with briefly introducing what Oakridge does, and go into the Gen 4 reactor development processes, particularly in terms of reactor core development, plant engineering, and licensing support, and safety analysis. And just a brief introduction about the Oakridge. Oakridge is a multidisciplinary engineering and consulting company based in Lyon, France. And we have active membership across the globe. Since 2002, that's when this company began. And we have partnership in 11 countries. And we are proud to say that we are the first company to attain ISO 19443 in France. So our projects are largely divided into new build and existing fleet. And for the new build, we do the basic design, detailed design and commissioning, and the subsequent license support to continue the operation of the new build. And the engineering and consulting services for existing fleet, we do O&M support, lifetime extension programs, and also the training of the workforces to continue operate in a safe and efficient manner. So when you look into the project portfolio, in the new build, we can, again, separate into SMR and advanced modular reactor development. So this portion come into play in about 3 or 4 years ago, before I came on board to Oakridge. So here are the clientele. We have a nice variety of regulatory agencies, power plant operators, and the OEM, and also the technology development companies such as KEPCO ENC, Advance. And you see on the bottom center, we have a group of Gen 4 reactor developers across the Europe. So we are in the active involvement with all these companies currently. This gives me an opportunity to showcase what we have done and what we like to do with these SMR developers across Europe and hopefully around the world. Okay, so I started my career as a scientist in Los Alamos National Laboratory in the US. So before I came on board to Oakridge, I actually had an experience in developing Gen 4 reactor types. So on my right, here's the high temperature reactor 10, which was a prototype that recently came on grid in China. So I simulated the burn-up scenario. And in Korea, the center photo, this photo is actually from Project Pele from US Department of Defense. But basically, you want to have a small microreactor on a truck bed that is mobile. And I did something similar in Korea for the Korean government. And now I'm in France, and I'm working directly with the Horizon for Gen 4 reactor, molten salt reactors. Okay, so we work a lot with the SMI developers, but obviously I cannot use their confidential information. So for this presentation, to showcase our capability, I simulated a prototype called Oak-1. That's our Oakridge prototype reactor. That's a thermal a molten salt reactor that is transportable in a truck bed. So reactor is approximately 2 meters tall with the active height of about 1.5 meter tall. And the reactor diameter is about 70 centimeters. Pressure is operating at 1 bar with a molten salt reactor fuel and temperature running at 920 Kelvin with hopefully the total weight of minimizing to about 40 tons. However, if you work with a microreactor at all, you'll realize the temperature management and also the weight management is very critical issues. So even if you get your reactor working neutronically, you really have to get down to the weight and heat management in order for the reactors to operate properly. So we are shooting for 2 megawatt electricity of power, maintaining criticality around 1. And hopefully the transporting dose or dose during transportation will be minimized to 20 millisievert per year. And we are looking at the nuclear fuel cycle of about 5 years. So that's the basic design goal we have in mind when we're trying to create this prototype reactor that is that can be on the road. So here is a rough picture, a movie of the reactor type we developed. You can imagine the inside of a container, and you have the core and the very basic reflector and also the moderator built in there. And of course, you have to have the primary loop and all the shielding and the cooling materials involved. So this will come out to be more elaborate detail when we are done with the design. So when we use the criticality calculation, you have to think about whether to design a thermal reactor or a fast reactor. But when you're talking about the modular reactor or micro reactor, you essentially negate the fact that you can go with the fast neutron reactor, because you're talking about neutron economy, and just being a fast reactor, you are wasting a lot of valuable neutrons. So you want to hold on to the neutrons as much as fission neutrons as much as possible. Therefore, you probably end up going with a thermal neutron reactor. Because this is a molten salt reactor, you have a choice of going thorium cycle, and you also have to think about the non-proliferation considerations. So what hasn't been done with this little exercise is the component sensitivity as to the reflector types and the shielding materials, and void temperature coefficient calculation, and the kinetic parameters will need to be verified before we are done with the basic design. The plot you see here in front of you is a combination of uranium-235, 20% enriched. So, we are using HALEU material, or by going the thorium cycle, we could use lower enriched uranium-233 and going with the thorium cycle. Anyway, so these are the considerations you can take advantage of. So here are some of the very basic nuclear physics, flux contour, capture contour, and also the elastic contour. The elastic in the reactor core or the moderator is very, very high, meaning there is a lot of thermalization of neutrons occurring in the core as we expect. So we can also perform the fuel inventory from the BOC, EOC, and anytime after the shutdown. So here are the isotope inventory that we could create. And also the radioisotopic inventory after shutdown. And also you have to think about the heat decay, or decay heat after the operation, because when you're working with the microreactor, you have to be able to manage the heat and be on the road moment's notice. So we characterize the heat dissipation process without the cooling system to observe how fast we could be mobile on the road with a shutdown reactor. So we are also concentrated on radiation protection calculations. So we have performed the those calculations during the operation and also during transport after shutdown. We realized that after shutdown, you don't have much of a neutron doses other than the spontaneous fission neutrons and also the alpha N reactions caused by the ones in the fissile materials. And also we performed some calculations in the fresh and the spent fuel in storage to design the storage facility as you see in this picture here. As it turned out, the hexagonal shape of storage facility is more effective in managing the area density of the spent fuel storage. So another big area of big area that we are contributing to the development is the plant engineering, thermal and HVAC, and also plant layout. So when you think about the thermal management for regular power reactors, you have much area to deal with, so that you have a lot of flexibility in dealing with the heat management. However, when you're talking about microreactor, you have to manage the heat well, and the thermal insulator design comes into a big play. So right now, the industry needs high heat resistant thermal insulator. So that's another area that we could focus on. So and also the HVAC, when you're talking about the regular HVAC, it's just a regular ventilation and flow. However, for nuclear power plant, the HVAC is actually needs to be contamination and controlled. And so the HVAC comes with the radioactive material control naturally. So plant layout, we also perform, I think Aurélien will talk about this a little bit, system design, fuel drain tank, fuel handling areas, fuel storage sites. We have performed these calculations and design to support these tasks. Licensing support. All the activities I described to you can also be included in the licensing support, because our basic design calculation results and our justification for our approach, and all those will be included in our licensing support documents. So we can do that for severe accident, early stages of PSA strategy, material studies, and licensing and regulatory support, and also providing supply chain. What you have seen on the slide right now is the what we actually performed for the severe accident scenario for a SMI developer. So I deleted all the sensitive information such as safety equipment, functions, and the consequences. But you could see that we go through every stages of failure, every possible mode of failure, and be able to come up with what could be the severe accident phenomena that could possibly occur with the preliminary design information we have. Okay, so that concludes my portion, and I give the mic to Cyrille.
Thank you so much, Dr. Chung. That was very clear, and thank you for the overview of all the things we do also for the Gen 4 reactors. And you've mentioned the role we have in early stage PSA. And for this topic, I will welcome to the floor the Vice President Samuel Sivault now. Thank you.
Thank you, Cyrille. Thank you, Dr. Chung. I want to say a few words about nuclear safety, because of course all the development that we do are compliant with highest standards in terms of safety. So the starting point is all the requirements from the International Atomic Agency, and we are capable to do some safety demonstration and safety analysis about the major topics. Radiation protection in design, of course, safety in design, defense in depth, and we are capable to demonstrate that the design will be capable to maintain the integrity of design of plant through the lifetime of the plant. This is very important. So, in terms of safety analysis, we are going to support the micro reactor development during the process of licensing with the regulator. Especially, we have a very long experience of analyzing the different criteria for the acceptance of the design. We are going to do some analysis about the transients, DBA, design basis accidents, that we are going to define and do the demonstration of safety, of the robustness of the reactor according to the different accidents that we are going to take into account. We are going to study the different accidents which are going to lead to containment pressurization, if we have some containment pressurization, of course. We are going to analyze all the pressurized thermal shock and the accident during shutdown of the reactor. And we have a special capability to do some severe accident analysis. For instance, we use the US code called MAP. This is for the deterministic demonstration of the safety. One very important thing is in Oakridge, for the last 10 years, would say, we have developed some probabilistic approach. And we are capable to do some probabilistic analysis and approach during the first step of conceptual design for the microreactor. So to give you an idea about our capability on these topics, we are currently involved for the lifetime extension of the Kiwhan nuclear power plant in South Africa. So for the safety demonstration regarding the regulatory requirements, we have involved a team of approximately 25 PSA analysts for 2 years to be able to develop all the external hazards and internal hazards PSA model and quantification of the core damage frequency. And I mean, about two years ago, we have started to take those methods for the microreactor development, and we are now capable to do some study at the early conceptual design step, including the probabilistic approach of the safety. Thank you very much.
Good evening, everyone. So maybe Cyrille want to make a word of introduction.
Introduce you, yes, sorry, I'm sorry. I'm late. Yes, thank you, Samuel, for this presentation. And now we will give the floor to our special guest coming from Narea, Aurélien Ledieu, who has the kindness to come today and to join our workshop, and also give a testimony of what Oakridge has done also at Narea. And so the floor is yours.
Thank you. Thank you so much, Cyrille, for introduction. So good afternoon, good evening, everyone. My name is Aurélien Ledieu. I am Narea owner's engineer. That means that I'm the overall design authority in Narea. I first want to, I'm very glad, and I first want to thank Cyrille and all the Oakridge Dream Team for inviting me for the present roundtable. And as Cyrille said, I'm not here to promote the nuclear salt, molten salt technology, because since it has been done by the previous roundtable with Nicolas, Isabelle, and Laure, it has been done. So I'm here to witness how engineering and consulting companies can be some partners to accelerate and secure the development of innovative companies such as Narea. So first of all, please let me introduce you briefly what is the business of Narea. Narea was created in 2020. We are staffed of more than 200 of people by right now, and our business model is energy as a service. Of course, it's decarbonized energy. And the second is to provide this energy from waste to energy. For that sake, we are developing an advanced modular reactor technology, which is called XAMR technology, based on chloride molten salt technology and fast neutrons. Thus, we develop simultaneously innovative technology relying on intrinsic safety, capability of industrialization with a modular approach settled in containers, and long-term contracts with our future customers. I will lastly add that we target the whole chain of value from fuel closure to energy delivery. Energy delivery could be thermal and electrical, as said in the previous roundtable, with a combined approach from R&D and operation and maintenance. So now let me show you and testimony how the multidisciplinary capacities of Oakridge had fastened our studies, and I have chosen two illustrations of support which have been performed in 2024. It was a selection, of course. So the first one is system engineering support Oakridge provided to our advanced conceptual design stages in order to help the design of fuel draining and decay heat removal systems. So Benjamin, who was involved in these studies, he was a senior fluid consultant, performed preliminary functional studies, performed also failure analysis studies, and of course help us in order to have the better option in designing or subsystems in those systems of involved major system of safety. All these deliverables were very completely relevant, and the support was very appreciated of Benjamin. The second delivery was dedicated on a more operational support, focused on the design and the early stage of the procurement of one of our major experimental mock-ups, a forced convection loop, as you can see on the picture. In that scheme, Emmanuel, which was the engineer involved in the study, performed a very high value and efficient support in technical calculation as well as technical option assessments and document fields. As a conclusion, I would like to highlight the high reliability and adaptability of the staff of Oakridge. The approach, fully dedicated to project management and understanding of startup specificity such as NAREA. Finally, if I had only 2 qualities to keep in mind concerning Oakridge, it will be the mutual trust and the commitment for the benefit of innovative nuclear projects such as NAREA is bearing. Thanks a lot for your attention, and I'll be happy to answer to a question. And, Cyrille, I give you slide.
Merci beaucoup, Aurélien. Thank you for this. You are all welcome to visit the booth of Oakridge, which is C64. And then you will find on this stand, you will find at any hour, you will find fresh champagne, good innovative new goodies, such as Pink Flamingo, maybe you've seen before. And also you can discuss with our experts and maybe work with us soon. Thank you. If you have any questions, stay here and go to that second room, just close to this room. There's a room we can discuss. Thank you so much. And thank you for the speakers, for all the speakers.